Welcome to a screencast on ions and ionic compounds. Let's start by noting that elements in the periodic table are organized according to their properties. And in fact, elements in a given column or group have similar properties. For example, the elements in group 1, what are called the alkali metals, have properties similar to other elements in that column. Elements in group 2, the alkaline earth metals, have properties similar to other elements in that column. The halogens, column or group 17, have similar properties. The noble gases have properties similar to other noble gases, etc. Now, if we look at a specific reaction between two different elements, and this is going to be a reaction between sodium, which is a metal. It's a reactive metal. Here it's stored in kerosene because if it's exposed to air, it actually undergoes an oxidation reaction. Here is a kind of cartoon image of a sodium atom showing the electrons in the electron shells for a sodium atom. And if sodium reacts with chlorine, and chlorine is a green gas, it's poisonous, it's a warfare gas. And here's what an atom of chlorine looks like. Again, cartoon version of that. And if we combine sodium and chlorine and allow them to react, and if we heat them up a bit, it reacts fairly quickly, what we make is, so here's an image of the reaction taking place. Very bright kind of flame appears to burn. We get some sort of white powdery substance produced. And if we let it cool down, it turns out that what's produced by this reaction is what's called sodium chloride or table salt. And on an atomic level, what ends up happening is, here's a sodium atom with one electron in its outer shell. Here's a chlorine atom with 7 electrons in its outer shell, and it would actually like to have 8 electrons. And so what ends up happening when a sodium atom and a chlorine atom combine and react is we make what's called a sodium ion. So the outer shell electron has been lost from this sodium atom. It has one less electron. Since electrons are negatively charged, that means the sodium ion now has a positive charge. And then that electron, here it's shown as a red colored electron, ends up adding to the chlorine atom in its outer shell to give it 8 electrons instead of 7 in the outer shell. One extra electron makes that a negative charge, so this is what's called a chloride ion. This has a filled outer shell. The sodium ion has a filled outer shell, and the positive ion and the negative ion attract each other in what's known as an ionic compound. And this is at the heart of a certain class or category of chemical reactions where ionic compounds are formed. Now, in general, ions are atoms, or it could be groups of atoms, that either gain or lose electrons. And when they gain or lose electrons, they end up with an overall charge. So, for example, sodium, which is an alkali metal, ended up losing an electron. It therefore became positively charged. And chlorine ended up, which is a halogen, ended up gaining electron, and it therefore ended up being negatively charged. So ions are atoms or groups of atoms that gain or lose electrons, end up with an overall charge. It turns out that, like sodium, all of the elements in the alkali metals column end up liking to form or tending to form positive one-charged ions by losing one electron. And it turns out that that's because all of these atoms have one electron in their outer electron shell, which is relatively easily lost. The alkaline earth metals tend to lose 2 electrons because they have 2 electrons in their outer shell, and they tend to make +2 charged ions. Now, on the other side of the periodic table, the halogens tend to gain 1 electron and make a -1 charged ion. The chalcogens, things like oxygen and sulfur, tend to gain 2 electrons and make -2 charged ions. The pnictogens, which is the nitrogen column, gain 3 electrons and make -3 charged ions. The aluminum column tends to make +3 charged ions. That's a little less predictable. but that would be the most likely guess, column 13 or group 13. And then group 14 usually doesn't make ions at all. Carbon can make a -4 ion, but usually it ends up doing a different kind of bonding altogether. And then the transition metals, the elements in this chunk of the periodic table, will make positive ions, but the charges aren't that predictable, and they can make multiple different charged ions. So iron can make a +2 or a +3 charged ion, plus others. Chromium makes a +3, a +6, and quite a few others as well. So those are not too predictable, other than they'll be positively charged if it's a transition metal. One thing also to note, the noble gases, column 18 or group 18, tends not to make ions. They have filled electron shells. They're stable the way they are, so they don't gain or lose electrons. They just tend to not react. So noble gases are very unreactive elements because they already have stable electron configurations. They have filled electron shells. Now, other elements will readily make an ion. They'll readily react by either gaining or losing electrons until they end up with a stable or noble gas arrangement. So fluorine can gain an electron, and if so, it ends up with one more electron, which is the exact same electron arrangement as neon. That's nice and stable. Sodium can lose an electron. That gives it one less electron, which also ends up having the sodium, once it's an ion, having the same electron arrangement as neon, which is nice and stable. So this is going to be a driving force for a certain kind of reaction that forms ionic compounds. Some examples of ionic compounds. Sodium likes to lose one electron and make a +1 charged ion. Chlorine likes to gain an electron and form a -1 charged ion. Plus attracts negative. That's the ionic bond, the attraction between the positive and the negative. A +1 nicely balances off a -1 to make a neutral compound, and all compounds are neutral. So the compound that's formed is NaCl, 1 Na for 1 Cl, and we call this sodium chloride. Now, if we have a reaction between magnesium and fluoride and fluorine, then we note that magnesium tends to form a +2 charged ion. It's an alkaline earth metal. It tends to lose 2 electrons. Fluorine is a halogen. It tends to gain 1 electron and make a -1 charged ion. +2 charged magnesium attracts -1 charged fluorine. That's the ionic bond. But a +2 and a -1 don't balance off and don't end up being neutral. But if there's a second fluoride, then we have 1, 2 negative charges to balance a +2 charge from the magnesium. Overall, we get a neutral compound, and the formula for this would be MgF2. We have 2 fluorides for 1 magnesium ion, and this is called magnesium fluoride. One more example, lithium combines with nitrogen. Well, lithium forms a +1 ion. Nitrogen forms a -3 ion. So how many lithiums do we need to balance off a -3 charged nitride ion? Well, if we have 1, 2, 3 lithiums, we have 3 positive charges. That balances off 3 negative charges due to the single nitride ion. So our formula will be Li3N, and this is what's called lithium nitride. And note, as a general thing for ionic compounds, we're usually going to be having a metal, like lithium, bonding or combining with a nonmetal, like nitrogen. The metal will make a positive ion, the nonmetal will make a negative ion, and then the positive and negative ions attract to make ionic bonds and form the compound. And the total charge that's positive and the total charge that's negative has to balance out, and that'll end up giving us our ratio of positive to negative ions, and therefore our compound formula. Okay, so a little bit of a summary here. The positive ions are also what are called cations. The negative ions are also called anions. and the positive and negative ions, or the cations and the anions, attract each other, and they combine in ratios that will give an overall neutral ionic compound, as seen in some of the previous examples. Here's a crystal, or a little piece of a crystal of sodium chloride. The green spheres represent chloride ions, negatively charged. The purple spheres represent positive sodium ions, and positive attracts negative. And notice here's a little, fundamental unit of this. But if we continue in all directions, it's always going to be positive ion, negative ion, positive ion, negative ion, positive ion, negative ion, going this way, positive, negative, positive, negative, positive, negative, and etc. So we have this big array of positive and negative ions kind of alternating in our what's called crystal structure of the ionic compound. Okay, so a little bit more with ionic compounds. How do we name them? And it turns out that the rules for naming ionic compounds are as follows. We write the name or say the name of the metal first, and then we say or write the name of the nonmetal second. And the metal name we leave alone, we don't change it. The nonmetal name, we change its ending to IDE. So, for example, if our ionic compound is formed by the reaction of calcium with bromine, calcium's a metal, bromine is not a metal. Calcium makes a +2 ion, bromine makes a -1 ion, so we need 2 -1 ions to balance 1 +2 ion. The formula would be CaBr2, and then the name would be calcium. We leave the metal name alone and we write it first, and then bromine we write second, but we change its ending to IDE, so bromide. So the overall name is calcium bromide. If we do a reaction between aluminum and oxygen, then aluminum's a metal, oxygen's a nonmetal. Aluminum tends to form a +3 ion. Oxygen forms a -2 ion. And to make everything balance, we need 2 of the +3 ions to balance 3 of the -2 ions. So our formula will be Al2O3, and then the name would be aluminum oxide. Aluminum stays the same, oxygen turns into oxide. And note, we don't write anything in the formula indicating the 2s or the 3s. We don't say di or tri or mono, because for ionic compounds, we know the charge the ion will form, therefore we know the ratio, and so we don't have to specify how many aluminums or how many oxides, because any self-respecting chemist can figure this out. Okay, now a complication to this. There are lots and lots of compounds that contain what are called polyatomic ions, which are groups of atoms that have an overall charge for the group of atoms. And there are lots and lots of polyatomic ions. Here we're just going to mention a few. So ammonium is the polyatomic ion of 1 nitrogen, 4 hydrogens, and the total of that 1 nitrogen and 4 hydrogens has a charge of +1. Hydroxide is 1 oxygen, 1 hydrogen, bonded together with an overall charge of the group of -1. Nitrate is a nitrogen and 3 oxygens with an overall charge of -1 for the whole group. Similarly for sulfate, carbonate, and phosphate, showing the respective numbers of oxygens and charges for each of those. There's not a great rhyme or reason to how many oxygens, at least at this point, for a given carbon or phosphorus or sulfur. So these are things you're just simply going to have to look up or try to remember. And we deal with these in the same way as we did not polyatomic ions. So for example, sodium carbonate, what's the formula? Well, we know sodium makes a +1 ion. And if we go back a moment, we see that carbonate is CO3 with a -2 charge. So sodium carbonate is going to need 2 sodium atoms, each with +1, to balance 1 carbonate with a -2 charge. Magnesium nitrate Magnesium makes a +2 ion. If you look at the periodic table, you'll see where it's located and why that would be. Nitrate, we know, is NO3 with a -1 charge, so we need 2 of the NO3 minuses to balance 1 Mg with a +2 charge. And notice we don't show charges on any of our formulas once we've put the ions together. One last example, ammonium chloride. Ammonium is a positively charged ion, NH4+. Chloride is a negative ion, Cl-. So one of each gives us NH4Cl for ammonium chloride. Now for transition metals, as we saw before, the charge of the ion formed, so these are the metals from groups 3 through 12, the guys in this part of the periodic table. The charge of the ion formed is not very predictable, and in fact it's variable. So to deal with this, we use a Roman numeral to indicate the charge. So for example, iron can make fairly commonly a +2 ion or a +3 ion, and other possibilities as well, but those are the most likely. Well, if we have a +2 ion, we say the name as iron, Roman numeral 2. If we're dealing with the +3 charged ion, we say iron, Roman numeral 3. And that holds for any transition metal. We use the Roman numeral to indicate the charge if there's some doubt or variability as to what the charge would be. For calcium, we don't use a Roman numeral. We know the charge will be +2. For sodium, we don't use a Roman numeral. We know the charge will be +1. But for transition metals, we don't know the charge necessarily unless we know the formula or unless we're given the name. So a couple examples of that. Copper 2 chloride. Well, copper Roman numeral 2 means we're dealing with the copper ion that has a +2 charge. Chloride has a -1 charge, so it takes 2 chlorides to balance off 1 copper Roman numeral 2, and the formula is CuCl2. Tin 4 oxide. Well, oxygen makes the -2 charged oxide ion. If tin has a +4 charge, we need 2 -2s to balance a +4, and so the formula for this would be SnO2 for tin 4 oxide. Here's a formula. Let's come up with the name. Well, PO4 is a polyatomic ion. It has a charge of -3, and you have to look this up if you don't happen to remember. If PO4 has a charge of -3, that means Fe must have a charge of +3. So we know we're dealing with the Fe +3 charged ion, so we write that as iron, Roman numeral 3, and then PO4 is phosphate, and that's the name of that compound. And that's it for ions and ionic compounds.